Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience, who would be curating the RealSci_Nano Twitter account.
Hello everyone, today we have with us Georgina Zimbitas, who is a postdoctoral researcher at the University of Strathclyde in the UK. Hi Georgina, how are you doing today?
I'm doing really well, Pranoti. How are you?
I'm good. Let's talk about your science, or rather your scientific journey so far. So how did you end up in your current research field?
It's been a long trip. So I basically started out interested in science as a kid. The first money that I was given to buy myself a gift with was when I was 8, and I bought myself a microscope, which I actually tore apart to modify it and make it into a projector so that I could project what I was seeing in the microscope to my poor family that had to endure my presentations. So science has been something I've always been interested in as in a kid. And I ended up doing a PhD. Well, first of all, I did my undergraduate in Australia at RMIT. I went to Greece and did a 4th year undergraduate to get an equivalent degree. I then moved to the UK, to the University of Liverpool, and did my PhD in surface science, which I realized is a passion of mine, just interactions that happen on surfaces and interfaces. And that's been with me throughout my whole career. Right. After that, I've basically just been in engineering departments, and mainly materials and chemical engineering departments. So I then went and did a postdoc at TU Delft in the Netherlands. And this had to do with internal precipitation within metal alloys. So it was materials and how we can modify them to make them more robust. I then moved back to the UK, to the University of Birmingham, where I was looking at thin films and viscous liquids and how to form thin films from them. And because I've done all these interfaces and, gas, solid gas, etc., I ended up thinking, well, let's go into the bulk as well and see what happens into the bulk, which is how I ended up at the University of Strathclyde and looking at small organic molecules and how they behave in water. So that's my current position, and I'm looking at how these small organic molecules actually form very loose aggregates in water that can be detected as entities that exist, and these are nanoclusters.
Interesting. So basically building, or rather changing or modifying the microscope into a projector at the age of 8. Now looking at nanoclusters, it's quite a broad journey you've had. That is so amazing.
But it's always looking at, what happens on a very small level. That's been my interest. Why does this happen? What is happening? So yeah.
That is amazing. That sounds super cool. So your current research, you did mention that it's about how these small molecules are forming aggregates in aqueous environments. So where do you see your current research fitting in this big picture of materials and nanoscience?
These small organic molecules that I'm examining at the moment are used often in producing nanoparticles such as magnetite and silica. If we can understand how they behave on their own, then we can actually transform that into how they can behave and modify the production of the nanoparticles of interest.
Okay.
So what we're doing is we're examining what happens with these small organic molecules on their own, and then we examine how they interact with the nanoparticles of interest, so the silica, like I said, or the magnetite, and how they help us get tailor-made particles, transform these particles into something that we could, that can be bespoke, that can be made to order.
Huh. That's really interesting. It's quite fascinating. And it does sound to me that you're doing a lot of cool research projects and are involved in a lot of interesting research experiments. Um, if you have to pick one that you're most proud of, or the most fun or quirky one, I know it's difficult to do that because all your projects are close to your heart, probably. But if you have to pick one, could you pick one of your research projects and explain it to us in the section we call In Other Words?
You're right. It's really, really difficult to choose one. I mean, all the projects I've been lucky because all the projects that I've been on have actually just grabbed my attention. They've just been fantastic and they've helped me move along. But if I had to choose one, it would be the one that I was most creative in. So the one that I was given the most freedom to modify and do what I wanted to do. And that would have to be the project that I was doing at the University of Birmingham, whereby I was given viscous liquids and asked to investigate if these liquids could foam, if they could produce a foam. And I came to realize that, well, foams are basically a series of thin films interconnected. We all know that. What about making thin films from these viscous liquids so I can study it from, the bottom level upwards to foams?
Right.
I designed and created and used my own freestanding film rig. So this was a freestanding thin film rig that I created, and I used it. There was interactions with glass beads to see how this thin film performed, the elasticity and various parameters of the film. And there was publication out as well that you can see the results of it. And I think I'm really proud of that because this project was mainly my input and my ideas and creating my own thin film rig and getting the results.
That is so cool. So is this similar to self-assembly?
That is a very good question. So these thin films were actually made out of surfactants and polymers, and water, and so there was a lot of phase separation going on and phase changing, and that's another thing. That's why I'm so proud of this project, because there's so many unanswered questions that I would like to take forward with me in research in the future.
Right.
And one of the aspects is to investigate any degree of self-assembly that is possibly actually occurring.
Okay. Oh, that is so fascinating. So basically, to summarize in one sentence, you created thin films out of nowhere. Is that safe to assume?
No, because there were surfactants. The probability of the thin films being created was quite high.
Right.
We didn't know the properties of these thin films, and we didn't know if they could actually create sustainable foams. And so the research showed that the possibility was very likely, and that these thin films had properties that we did not expect, such as the elasticity.
Wow, that is so cool. I can imagine why you picked this as part of the most proud of, because you basically worked on it from scratch, and you had the freedom to do it, and you did do it, and there is still a lot of unanswered questions. It's still quite interesting.
Exactly.
That is amazing. That is so cool. That's amazing. I need to digest this amazingness of this science that you just said.
This is one of the projects, like I said, that I want to take on and move forward in the future. So this is the direction, creating materials and self-assembly of thin films, and using this as a template for self-assembly.
Okay, all right, okay, super. So hopefully your next project, or the one after next, could be about this, or the next step of your work.
Yes.
Fingers crossed.
Fingers crossed. It's my project that I will be involved in and in charge of. Yes.
Super, super. That's wonderful. Georgina, let's talk a little bit about the other parts of most of the researchers' life, usually in the academia, which is teaching the next generation, making next generation of scientists, basically. So, do you teach? And if you do, which courses would you like to mention?
So, way before I became an academic, I was actually a teacher. So, yep, I had a license to teach, well, I still do, have a license to teach English as a foreign language. So I actually taught English while in Greece. I
Right.
also taught high school chemistry.
Okay.
So teaching has been with me throughout my career, and even when I wasn't given the opportunity to teach in academia, I would basically demand it. So I've been this is one part of academia that I absolutely adore. I love research. I love molding the minds of the future researchers, and I especially love instilling in them the ability to become independent researchers, to stand on their own ground, to feel confident, to speak up, to express their opinions, to use critical thinking. I find this fantastic. This is part of academia that I absolutely adore. So I've done various classes, and they've mostly been in physical chemistry, but some of it has been also in the engineering department. So most of it's been around about crystallization, which features heavily in my work. Phase diagrams, thermodynamics, a lot of maths for physics, physical chemists, a lot maths for chemical engineers, etc. And the last class I taught, which was recently, was MATLAB basics, so the use of MATLAB.
Ah, that is just it's as diverse as your research projects. I feel your teaching activities are as diverse as your research projects so far, like starting from English to chemistry in high school, and it's just so fascinating. It's so amazing.
I think the process is that I get to learn as well. So,
Right.
I mean, I think the best teachers are the ones that actually learn from teaching. So, me, just I learn from it. So it's fantastic.
Ah, that's amazing. And I also love the fact that you want to teach the students, but you also want to make them independent. You want to instill this independent thinking and that sort of culture that you want to cultivate. That's
Exactly,
amazing.
exactly. We need confidence. We need these students to have the confidence, especially when it comes to young females. We need to for them to be able to speak up. All of them, students, female and male, speak up, express their opinions. So many people are being stifled because they feel embarrassed to talk, and they've got great ideas. And to be honest, your idea is not going to fly if you never express it.
Yeah.
So go ahead, stand your ground, speak up. We want to hear your opinions.
Yeah, that is true. That is so nice. That is, I hope most of the teachers or all of the teachers are thinking like you. All the researchers, especially who are teaching, are thinking like you because this is really, really important. Georgina, let's move away from the teaching and focus, or rather, zoom out a little bit and look at the research experience in as a whole. Um, I hope your experience so far has been wonderful and will continue to be wonderful in the future. However, if you have three wishes to improve your research experience, what would you ask for? And I'm not promising anything here.
Oh, if you were, honestly, I would ask. But yeah, from a personal level, and this is completely personal level, I would like some stability. So at the moment, as I've expressed, I've moved quite a lot, and I've done quite a lot of things. So I've been involved in administration and citizenship and teaching and research, and I've done, like I said, quite a lot. Yet I don't know where I'm going to be in the next year or the next 2 years. So this kind of prevents me from developing ideas that I want to, because I have to focus on other things. And I do have quite a lot of ideas in my mind. So for me personally, I would like some stability. I would like to know that this is it. This is where I'm staying. This is the permanent job. I can now focus on elaborating my research on a personal level. Another thing that I could mention is funding. It's more difficult for some to get funding than others.
Yeah.
The statistics. I'm not going to go into who, what, whatever. But the fact remains that some people are disadvantaged, and academia has actually leaned heavily on funding being one of the most important aspects of progress. Like I said, it's not always fair. Some people are disadvantaged because of background, because of other reasons. And not only that, it could be the research they're doing. Blue sky research isn't as heavily funded as, let's say, more industrial-based research. So I think there needs to be something, a different approach to how we act towards funding, to have, especially when it comes to promotions. Last but not least, and definitely not least, is transparency. There are too many articles you read, and you read them and you're thinking, this is amazing if only it were true, because I can't believe it. I can't see how they did this reaction, or there's things missing.
Right.
We need some more transparency, and this has led to a lack of trust in science, and this is unfortunate. I mean, this is not right. So I really think more transparency is needed. I understand sometimes there are things put in place to avoid, because of patents and stuff. I understand that. But when people are claiming breakthroughs and you can't see the raw data, or you can't even see how, you can't replicate the experiment because information is missing.
You're right.
Red flags, I'm sorry.
Yeah.
And I'm seeing a lot more of this lately, which is unfortunate.
Okay. Yeah, I wish I could just be like, okay, tomorrow when you wake up, Georgina, it's going to be I'm going to grant all your wishes. I know it would be fantastic. I know, I wish I could do it. But I mean, I feel you completely. I mean, stability is extremely important. In order to work on an idea, you can't really work on an idea properly without freedom if it's always the back of your head is like, oh shit, 2 years, 3 years, and then I have to move on to the next thing. I mean, in some way maybe it adds the dynamic side to the research, but most often than not it hampers the productivity, because you are always thinking, oh, how long I have to make sure I have a job in 3 years or 5 years, however long the project is. So stability is extremely important. Absolutely. And with the funding, I completely agree that we need different funding structures or parameters when evaluating research proposals, researchers as well. I think it's extremely important because as you correctly pointed out, it's not fair. It's not fair. And it's the statistics. It's not something that we are just saying out of.
We're talking about statistics. We're talking about facts. We're not talking about,
it's not a feeling.
It's not a feeling. It's not even personal. We can see it. The statistics are there.
Yeah, absolutely, absolutely. And the transparency. I think this is extremely important, because reproducibility and being honest about your results is extremely important. And I wish every scientist, every person who's writing a manuscript writes the experimental part, at least write the experimental part in as much detail as you can, so that person sitting across the world can reproduce with the same setup or similar conditions to some extent. It might not be 100% reproducible, which is absolutely fine, but to a certain extent, just like even like 50%. I don't know.
I mean, that's how you move science forward, by reproducing something and then taking it a step further. If you can't even reproduce it,
then you have to start all over again.
Something's wrong here.
Yeah, something's absolutely wrong. Yeah, you're absolutely right. I wish I wish I could just grant all of these wishes, and be like, yes, that's what we are going to do. But I think it's safe to, or rather, we can only hope that we are working towards it. That in the near future we will have stability and better funding structures and more transparency and trust among the scientific community, because it's extremely important. You're absolutely right. And speaking of future, what are you most looking forward to in the next 3 months?
I am currently in the process of finishing 3 articles.
Ooh.
Yeah, I'm very excited about all 3. They all have to do with nano-sized elements, but they're all different. So one of them has to do with, it's a theoretical paper that I've been part of, where I modified a model and rewrote it in MATLAB.
Mm-hmm.
I'll correct myself. I didn't modify the model. I took the model and rewrote it in MATLAB
Okay.
to make it more to prepare it in a platform that's more user friendly.
Mm-hmm.
And that looks at persistence length via a use of DLS, dynamic light scattering.
Right.
The other paper has to do with magnetite nanoparticle production.
Okay.
So that's that one. And the third paper has to do with silica nanoparticle precipitation. So hopefully they'll all be submitted within the next 3 months. I'm looking forward to these 3 papers.
Oh, that's a lot of interesting science that you're like. I'm gonna cross my fingers that everything goes through without any revisions or minor revisions. Let's say minor revisions.
Let's be as realistic as possible. Yes.
Yeah.
Exactly.
May not be like completely yes, we want this, but minor revisions are also okay.
Oh yes, yeah, that would be a dream come true, indeed.
Wonderful, wonderful. So before we let you go, Georgina, what I want to understand from you is, what are the challenges faced by the field of materials or nanoscience? The big questions that the researchers are trying to resolve.
I'm going to talk about mostly the area that I'm working in at the moment. And in my area, it has to do with precise characterization of nanoscale particles as they're forming.
Mm-hmm.
So, I mean, it's already difficult to see these nanoparticles once they're formed. So
Right.
it's even more difficult to see what happens as they're forming.
Right.
We need to understand what's going on. With regards to my research, I mentioned silica and magnetite. Silica magnetite nanoparticle industry is it's a $1 billion industry at the moment. And yeah, we use magnetite in medicine, in medical technology. These are particles that are necessary for X-rays, etc. Magnetic resonance, MRI. Sorry, that's what I meant. So they use an MRI, and like I said, it's $1 billion industry.
Mm-hmm.
So sorry, I'm just going to start that again because I didn't like the way I did that. So you can cut that out.
Right. Okay. Do you want to start the answer? Do you want me to ask the question again?
No, you've already asked the question, and I'll just go from the answer. So, I'll start now.
Okay.
So, precise characterization of nanoscale particles as they're forming is very, very necessary to look at. We can barely identify the existence of these nanoparticles, let alone understand how they form, and we need to understand how they form. The reason why we need to understand this is because these particles are used quite a lot in industry, nanotechnology, biotechnology, medical technology. An example of which I mentioned before, which was magnetite and silica. And these two nanoparticles are $1 billion industry particles.
Mm-hmm.
The production of these particles is very low. We need to scale up. In order to scale up, we need to know how they're produced, how we can make them bespoke, how can we tailor make them, etc. And we can't do that unless we understand how nanoparticles are formed.
Mm-hmm.
So this is eluding us at the moment. More research needs to be done at this level. And at the same time, if we know these things, we can change various parameters, and the most important ones being sustainability.
Mm-hmm.
The production of these nanoparticles that I mentioned is extremely wasteful. Not only energy wasteful, but solvents, materials. There's just too much waste.
Mm-hmm.
This is ridiculous.
Right.
Material science needs to be more sustainable. It needs to be more green.
Yeah.
So research needs to be done in this area, and we need to move towards sustainability.
Okay. Yeah, you're absolutely right. If you want to scale up the production of these nano particles or nanomaterials, then it can't be at the cost of 100 liters of acetone for few milligrams of nanoparticles. It can't be. It's not sustainable.
The whole point of one of the points of material science is the betterment of human life.
Right.
If we're ruining the environment, we're not going to have a better life.
Right. That is true.
That's a contradiction of terms. So we really need to make sure that we're making products that are sustainable, that are not impacting the environment, and are yet as good as any other product we've made.
Yeah, and then it is worth it, right? Then it is worth all the effort that we are putting in and making the nanotechnology actually be part of our real life, like coating your, I don't know, tables or whatnot.
Exactly. Yeah.
Okay, wonderful. So yeah, that's quite an interesting challenge. I never thought about it. Honestly, I never thought about it. Like how much effort goes in, how much energy and material goes into making tiny amounts because
Yes.
it's tiny.
It
It's nano.
That's absolutely. You're making tiny particles at tiny amounts. Exactly. That's it. Yeah.
Yeah. So yeah, that's a very good point. It would be great to have that. Yeah, that's a very good challenge. You're absolutely right. I'd never thought about it. So thank you for showing material science in a different light to me as well. So thank you, Georgina. This has been lovely. I enjoyed learning about your science a lot, and I feel like I know you a little better now. Thank you very much for speaking with us, and we are very excited to have you on Real Scientist Nano.
I'm excited to be here. Thank you, Pranoti.
Thank you for listening. To know more about us, please visit our website realscientistsnano.org and follow us on Twitter at realsci_nano.